Hi everyone. In this lesson, we're going to go over continuous probability distributions, and we're going to look at a particular example called the uniform distribution. Now, for a continuous random variable x, the distribution of outcomes is now going to be defined by some function, y equals f of x. That's for continuous random variables. Now, we use this f of x function to define probabilities as we have shown down here. Now the function y equals f of x has to have two properties, and those properties were defined on a previous slide, so please read through that slide carefully. One of the properties is that the function must always be bigger than or equal to 0. As you can see, we have pictured here a typical function like this. You see it's above the x-axis. And the total area bounded between the graph of the function and the x-axis down here must be 1. And what that means is that the probability that the random variable x occurs between negative infinity and infinity is 1, which naturally has to be the case. Now the way we use the function f of x to define probabilities then is like this down here. So we say that the probability that x falls between two values, c and d, is just the area bounded underneath the graph of the function and above the x-axis for x between c and d. So you see the probability that x falls between c and d is this area that we have shaded right here. So that's how we use functions to define probabilities when our random variable x is continuous. Now it's also important to note, and this is talked about in the previous slide, that for continuous random variables now, the probability that x takes on exactly one value is always 0. So we no longer talk about the probability that x equals 5, for example, because that's always going to be 0, no matter what value we have here for k. And that's because if we look at a graphic over here, you see, if I pick a value k right here, well, the area underneath the curve, well, that's just the area of a straight line. Well, the area of a line is 0. So that's one way to think about it. And another way to think about it is, if x is a continuous random variable, then that means that x can take on infinitely many values. Well, the probability that it takes on the exact value of like 5.32894, and so on, well, it makes sense that that should be 0, because x can take on infinitely many values, and that would be one of those infinitely many values. So we no longer talk about this type of probability anymore for continuous random variables because it's always 0. Instead, we talk about probabilities like the probability that x falls between two numbers. And that's going to be represented by the area underneath the graph of your function f of x. And that function f of x is called your probability density function. Now also note down here that it doesn't matter whether we use less than or equal to symbols when we talk about these probabilities here, because these two probabilities here are equal to each other. So it doesn't really matter whether we use less than or equal to for our problems. Normally we'll use just less than, however. Now let's take a look at the uniform distribution. Now the uniform probability distribution is the simplest type of distribution for a continuous random variable. And the distribution is rectangular in shape, and it's represented by a function like this. We call this a piecewise defined function. And for x between the values a and b, the function f of x is simply equal to this constant, 1 over b minus a, and it's 0 otherwise for x less than a or greater than b. Now right here we have a graph of a typical uniform distribution function. So you see the function is 0 for x less than a. It's equal to 1 over b minus a for x between a and b. You see right there is the value 1 over b minus a on the y-axis. And then it's 0 for x greater than b. And the area underneath this rectangle must be 1. Now the reason that the height of this function here is 1 over b minus a is exactly because this area has to be 1. You see, if we label this height here, call it h, then remember the area of a rectangle is width times height. Now this distance right here, this width, is b minus a. And so in order for this area to be 1, we need that b minus a times h. That's going to give us the area of the rectangle. That must be equal to 1. And solving this equation for the variable h, we simply divide this to the other side, and we get that h equals 1 over b minus a. So that's why this height here must be 1 over b minus a. And of course 1 over b minus a times b minus a gives you back 1. Now once again, the probability that the random variable x is between two values c and d for a uniform probability distribution is then just going to be this area that we have shaded right in here. Okay, so it's just the area underneath the graph of your function from c to d, and in this case it's just going to be the area of this rectangle right here. Now let's take a look at a few properties of the uniform distribution. Now here we have a few facts about the uniform probability distribution. As mentioned before, the uniform distribution is defined by this function right here. We already discussed that. It's also useful to note that the mean of the uniform distribution is given by a plus b over 2. Now that makes sense if you think back to what the graph of the function looks like. Let's just take a look at that again. Here's the graph of a typical uniform distribution, and a plus b over 2 is going to be the exact midpoint right there. So that point right there is our mean mu, and it's equal to a plus b over 2. That's from the midpoint formula. So it makes sense that this should be our mean because it's directly between a and b, and we have this nice symmetry of this function around the midpoint a plus b over 2. So it makes sense that our mean should be that midpoint a plus b over 2. Now this isn't as obvious to see as the mean is for the uniform distribution, but the standard deviation for the uniform distribution is given by this quantity, the square root of b minus a squared over 12. Now we can prove that mathematically, but that would be beyond the scope of this course. But that is what the standard deviation is equal to for a uniform distribution. Now let's take a look at an example. Now in this example, Southwest Arizona State University provides bus service to students while they're on campus. A bus arrives at the North Main Street and College Drive stop every 30 minutes between 6 a.m. and 11 p.m. weekdays. Students arrive at the bus stop at random times. The time that a student waits is then uniformly distributed from 0 to 30 minutes. And the reason it's going to be uniformly distributed is because students arrive at random times. So we have these questions to answer. Let's draw a graph of the distribution. What is the probability a student will wait between 10 and 20 minutes for a bus? What is the probability that a student will wait more than 25 minutes? And then how long will a student typically have to wait for a bus? In other words, what's the mean waiting time going to be for students? And then what is the standard deviation of the waiting times? Now here's our answer for part A. So we're going to let x, the continuous random variable x, be the waiting time for a student. Now note that x is going to be between 0 and 30 because a bus arrives every 30 minutes. And the function defining the probability distribution is then going to be this. You see, in this problem right here, the a is 0, so that's our a, and the b is 30. So our probability distribution is going to be 1 over b minus a. Right here is b minus a. And that's going to be for x between a and b. And it's going to be 0 otherwise. And so then the graph of this probability distribution is as we have shown down here. You see right here is a, right here is b. The height here of the function is 1 over b minus a, that's 1 over 30, and 0 for x greater than 30, and 0 for x less than 0. So there you go. So that's our function right here. Now let's take a look at part B. So the probability that a student waits between 10 and 20 minutes is going to be the area underneath our probability function for x between 10 and 20. So it's going to be this area that we have shaded right here. So how do we calculate the area of a rectangle? Well, it's just width times height. So you see the width here is 20 minus 10, so that's 10. And the height here, that's 1 over 30. So the probability that a student waits between 10 and 20 minutes is going to be 1 over 30 times, this is 10. And so that's going to be 1/3 or 0.333. So about a 33.3% chance that the student will wait between 10 and 20 minutes for a bus. That's all you have to do, calculate that area. For part C, we want to find the probability that a student waits more than 25 minutes. Now, a student isn't going to wait more than 30 minutes because a bus arrives every 30 minutes, so basically we're finding the probability that x falls between 25 and 30. So that's going to be this area that we have shown right here. So we have to find the area of this shaded rectangle that we have here. Well, the width is 5 and the height is 1 over 30. And so the area of this rectangle is 5 times 1 over 30, or 1/6, or 0.167, or about a 16.7% chance that the student will wait more than 25 minutes, which is the same as the student waiting between 25 and 30 minutes. Now for part D, we want to find the typical waiting time for a student. Well, that's the same as asking what is the mean waiting time for our distribution that we have pictured down here. Well, recall the mean is given by this quantity right here, a plus b over 2. And in this case, 30 plus 0 over 2 is 15. So right there is our mean. So that is the mean waiting time for students. And the standard deviation, recall, is given by this formula right here. So in this case, that's just going to be the square root of 30 minus 0 squared divided by 12. And you can evaluate that on your calculator, and you'll find that it is 8.66. And so we have then found our mean and our standard deviation. And that concludes this video about the uniform distribution.